Hi, I'm Creedy, and this is my MouseTrap project for physics, and this is a video of my car, which didn't exactly work out so well. So I used my friend's data and her car. I used my friend's car, but this is me actually making the car and putting effort into it. Throughout, throughout the day, and I'm gonna start off with my elastic energy. So, which is the energy stored in the MouseTrap screen, and this is the graph of me finding the elastic energy within the spring of my MouseTrap, or of the cars that I use MouseTrap. And so in order to find the elastic energy, let's go to PDF here. In order to find the elastic energy, we have to solve for the area under the graph. And it was applicable, so we solve for the triangle and the rectangle. And okay, I just realized I did something wrong here. Right here, I forgot to divide by 2. So it's 1.3 divided by 2, and I can just pull up Excel real quick and solve for that. So let's pull up Excel. Okay, so it was 1.3 divided by 2, so that's that. Let's see. This is correct, I believe so. And 0.06 is the time, the displacement basically, is delta x. And it was 0.19, so it's that plus 0.19. So that was the exact elastic energy. Let's write that down. Elastic energy. And so now that we have elastic energy and I've corrected my mistake, let's show you my position versus time. So this is Kim's data, or like the data from Kim's car, and the top graph, the red with the red curve, which is the acceleration deceleration, is position versus time graph, and the mass of the car is, now we have to talk about the mass of the car so we can solve for stuff. So we had to convert to kg, and this is how it looked like, and we found the mean, or the average, which is 2.4, so 1 kg equals 9.8 newtons. So our answer was 0.24. That's how we found the mass. And maximum velocity and kinetic energy, and I can explain this to you. So basically, if you look at the graph here, this is it speeding up and slowing down. So what we did was so as it goes up, which is not this one. Okay, this one's for deceleration. This for kinetic mass 0.24 times, so it's mv squared divided by 2, and so it's kinetic energy of speeding up, so 5.6 times 5.6. And then you have to divide that by 2, so our kinetic energy speeding up is that. And our kinetic energy slowing down is 0.24 times 0.4 times 0.4. And you have to divide that by 2. And that is our kinetic energy slowing down, decelerating, and so we have that out of the way. Acceleration is basically the slope of the graph, as you can see here, slope, because acceleration is for every second, how far does something move every second, per meters per second, whatever. So, and our force diagram, let's go to our second PDF page. So our force diagram for speeding up or ignoring air, so velocity and acceleration are both going towards the right, my right, and that's basically how we're going to figure out how to find friction, because second law applies here. Normal force and weight are equal, and then friction is to the right because of acceleration. As you see here, we draw, as we draw this force diagram, so weight goes down. Okay, let's start with normal force goes up, friction goes that way, weight goes down, and then MA goes that way because it's the head of where we start and end of that. So basically, because of first, we're basically following the second law. So force equals MA, and then it's 0.7 because that's the slope, because acceleration is the slope, mass is 0.24. So our sum of forces equals 0.0160 for speeding up, and for slowing down, it's the same thing, but friction's in the opposite way because acceleration's in the opposite way. So it's the same thing. It has friction equals MA, second law, we have to follow it. Instead, and slope is negative 1.4, so sum of forces equals 0.336. So we have force diagram and total force out of the way. Now energy flow diagram. Energy flow diagram, we started off with E elastic equals max, velocity equals 0, and then it was velocity equals max. So we have E elastic in the first stage and then kinetic energy into the second stage. It's completely loaded right here, and energy dissipated. So as you can see, we basically found an equation. We derived an equation, and E disk equals EL minus EK, and because our EL was wrong, our E elastic was wrong, let's just resolve this again. So that's our E elastic, and we have to use our, so E elastic minus our energy, and that is the amount of energy dissipated in the 2 moments in time. And I didn't do the V-Python,